for joining our third webinar in our 5-part Open-NFP Spring Webinar Series. Today, Professor Yan Liu and Xiaoban Wu are going to present network measurement with P4 and C on Netronome Agilio. In this webinar, Professor Liu and Xiaoban will implement and evaluate the count-min sketch using the combination of P4 and C on a Netronome NFP-based SmartNIC. They will demonstrate the flexibility and performance of the design and the C plug-in feature of the Netronome NFP. A copy of the presentation, archived replay, as well as any project code will be made available shortly after the webinar. These, as well as our previous webinars, can all be found on the classroom page of the OpenNFP.org website. Yan Liu is a professor of the Department of Electrical and Computer Engineering at the University of Massachusetts Lowell. Professor Liu's current research focuses on heterogeneous architecture and systems, software-defined networking, and deep learning. He and his team aim to design novel architecture and systems to facilitate programmable networking, deeply embedded sensing, and healthcare applications. Xiaoban Wu is a PhD candidate in the Department of Electrical and Computer Engineering at the University of Massachusetts Lowell. He currently works as a research assistant at Advanced Computing and Networking Systems Lab with the research interest in the application of DPDK for network measurement. Let me describe Open-NFP before I turn it over to Xiaoban. Open-NFP's objective is to support and grow reusable applied research and technology development in data plane network functions processing. We do this by focusing on reducing the barriers to performing research in this space to researchers and developers creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, Open vSwitch, and P4. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and cloud access to development systems and direct support from our engineers and a research community. We also provide support to learning advanced networking concepts on our hardware through tutorials and seminars such as the one we are performing today. We encourage proposals to research funding agencies. We invite you to join the 40+ universities and companies working directly with Open-NFP through projects. Over to you, Xiaoban.
All right, this is Yan Liu from UMass Lowell. Before Xiaoban begins his talk, I just want to say a few words about our project. So this is one of our research projects in the ACNS lab. We are working on network measurement, which is important for understanding the network status, utilization, and also identifying network anomalies. We are focusing on network measurement. In particular, we want to achieve programmable measurement with programming languages and integration with software-defined networking to be able to measure dynamic metrics and on different targets. This measurement project is being funded by the National Science Foundation IRNC program. In this talk, Xiaoban will talk about one of the subtasks we are working on, which is using sketches to quantify the network metrics of high-speed network flows. In particular, in this talk, we will look at count-min sketch and to give us an introduction how we implement this on the Netronome NFP architecture. Xiaoban.
Thank you. My title is Network Measurement with P4 and C on Netronome NFP. I'm Xiaoban Wu. First, P4 is a high-level language for programming protocol-independent packet processors. And we have NFP SDK. It provides C Sandbox. So in this presentation, we want to use both P4 and C to develop some protocol-independent measurement functions. First, we know network measurement has been playing a crucial role in network operations since it can not only facilitate traffic engineering, but also detect anomalies. So for example, counting the heavy hitter and the number of unique flows can be used to detect DOS attacks and port scans. However, it is difficult to count in high-speed links. Hence, we usually resort to sketch, which requires small processing cycle on each packet and maintains a good approximation based upon probability. So we are going to introduce two measurement functions. The first one is heavy hitter. This will be approximated by the count mean sketch. And the next measurement function is the number of unique flows. It can be approximated by bitmap. So the first algorithm is the count mean. So before we run the count mean, we need to declare some global data structure. So first we have on the left side, first we have the flow. Usually flow is defined by the file tuple, source destination IP address, source destination port number, and the protocol. And sometimes we can also add source MAC and destination MAC into the flow. And then we need to define heavy hitter struct. It has flow information and its corresponding count. And then in order to run this algorithm, first we need to declare a global heavy hitter. We need to maintain it and update this one. And also we need to have this count mean sketch. It has 3 rows and n columns. Usually people pick like 3 to 5. The number of the rows determine the confidence bound, which is to what extent we want to trust the approximation. A number of columns is n. It will determine the error bounds. Usually, the more the number of columns, the better approximation it will be. So, and then we have 3 hash functions: #1, #0, #1, and #2. So, if we look at the flowchart on the right side, for each flow, and the very beginning, we will use these 3 hash functions to hash this flow. Suppose we end up with 3 hash values, HV0, HV1, and HV2. And then we use these 3 hash values as the column index. So then we go to each row and the corresponding column to read the value and increase the value and then write the value back. So when we do the increment on the value, if we focus on the packet count, we update this value by 1. And if we focus on like the packet size, the total traffic size, then we'd better add it by the packet size, which can be obtained from the IP header. So after this process, then we need to find the minimum of the 3 values. So we get a min, min. And finally, we need to compare this minimum value with this current maintained global heavy hitter count. If this is true, then we can assume that now this flow will be the new heavy hitter. So we update the heavy hitter.flow is this flow, and the heavy hitter.count is this obtained minimum. So this is the algorithm of the count mean. The next, so I will give you a process is with a matrix, detailed matrix. I'll show you how this works. So now let's suppose now we have a global heavy hitter. So before flow A comes, the current heavy hitter data flow is flow B, and the heavy hitter data count is 2. Now when the flow A comes, so first we apply 3 hash functions. We have hash 0, hash 1, hash 2. We hash this flow, and we got its corresponding column index. So for hash 0, we get the index is supposing it starts from 1, so we get a 3. And hash 1 gets 2, and hash 2 get index 4. Then we go to the corresponding row index and column index. We read those values. So suppose now they're 7, 4, and 2. And now if we focus on the packet count, we just increase them by 1. So then that would be 8, 5, and 3. We write them back. And then finally, we need to compare and find the minimum value from each row. So that's the minimum from between 8, 5, and 3. So we can see the minimum is 3. Now, finally, we need to compare this minimum with the current heavy hitter dot count. We can see 3 is more than 2 because before flow A comes, we know the current heavy hitter dot count is 2. So we can see 3 is more than 2. So now we know that now this flow A should be the heavy hitter, and so we update it, and then we update its corresponding heavy hitter dot count as 3. So this is how we use this algorithm, economy. So the next algorithm is the algorithm bitmap. So also we need to maintain a flow struct, and then in the economy we have 3 rows. Now in this bitmap we only need 1 row. It's 1D array. Now it has n elements in this sketch. And also we only need 1 hash function. Similarly, every time the flow comes in, first we hash it. Suppose now we hash this flow, we get a position value. So on the right side on this flow chart. Then we go to the position POS and mark then bit and then our element by 1. So sketch and position is equals to 1. And finally, after suppose sometimes we want to approximate the total number of unique flows, we can just count the number of zeros in this sketch. Let's say we find out n with z zeros in this sketch, and the final approximation is a number of unique flows can be approximated as n times ln parentheses n over z. So this is how this algorithm works. So next I will introduce an example. Suppose initially we have 4 elements in this sketch. So and they are all initialized by 0. Now after flow A comes, suppose the hash value is 1. So we go to the index 1, and we mark that bit by 1. So now we have 1 0 0 0. And after flow B comes, we hash B. Suppose then the hash value is index 4, so we go to the 4 columns and mark that bit by 1. And next, if flow C comes, if the hash value is also 4, we mark the bit the fourth element in this sketch by 1. So now you can see finally we have 1 0 0 1. If now we want to find out approximation of number of unique flows, we just count how many 0 in this sketch. You can see that's 2. And then finally, by the formula, we can calculate this approximation. That is 4 times ln parentheses 4 over 2. So by calculator, we can see that's 2.7. Now if we assume the flow A, flow B, and flow C, they are distinct, then we can see the real unique number flow is 3. And we can see the approximation 2.7. So this is a good approximation. So I just introduced the 2 algorithms. So now we want to focus on how to implement those algorithms on the national NFP. So before that, I want to talk about some restrictions of P414. So there is now another branch called P416. It is still under development. So when I talk about the restriction, it is referred to P414. So in this P414, it has some essential restrictions. First, the else statement can only be used in the control block. And the second is P414 doesn't support for loop. And the third is it has only limited set of primitive actions. So first, the restriction of P414 is the if-else statement can only be used in the control block. So this implies that we can not use if-else statement in the action body of P4. So now the question is, suppose we have 3 variables, A, B, and C in P4 program, And how do we determine the minimum of this ABC? So if we want to apply the if-else statement in the action body, we have in the control block, we have to apply the table. So we can declare 3 tables. We can call them table find a minimum 1, find a minimum 2, and find a minimum 3. And for each table, we need to specify each default action. So in the table find a minimum 1, we have its default action do find a minimum 1, which is defined by modify the D with A. Now let's assume the minimum is D. And similarly, we have default action do find a minimum 2 and find a minimum 3, which modify this minimum D with B and modify minimum D with C. So next, if we go to the control ingress block, first we can apply the first table, which means we want to assume now temporarily A could be the minimum. So we modify field D with A. And then we do a comparison between D and B. So if this minimum is more than B, okay, we can see, okay, B should be the new minimum. So we apply this second table, find a minimum 2. So which means we modify this D with B. And finally, we compare this current assumed minimum D with C. And if D is more than C, we can see we need to apply this last table, find a minimum 3, which modify this D minimum value with C. This is how we implement this in the control block. And also, if you want to run this pupil program, we need to populate this table entries to indicate the default action for each table. So some other extra work. So we can see that this scenario is actually one part of this counting algorithm, and you can see this implementation of this counting algorithm with vanilla P4 become tedious level work. So we just repeatedly in the control block apply the if statement, and also we need to populate the table entries. So how to work around this? So this is the restriction one. The second restriction is the P4 doesn't support for loop. Now suppose we have an array called AR of size 1024 with 0 and 1 in it. How to determine the number of 0 in this array? So if we want to try the similar approach like how we find a minimum before, then now we need to implement one table and 1024 if statements. So on the left side, we have that table. We call it has default action do ink count, which add a field, add to field to the count by 1. So every time this table is applied, this count is increased by 1. And then in this control block, if we want to try to find the total number of zeros, we need to go through each element in that sketch, right? So in each element, so first we check if the first element is 0 now. If it is, we increase the count. And finally, if 1023, that element is 0, we also need to apply this table. So you can see this scenario happens exactly in the bitmap algorithm. So you can see this is not very convenient for us. So now how to work around this? And the last restriction of P4 is that P4 has only a limited set of primitive actions. So now suppose we need a completely new P4 primitive so that we can put an elephant into a refrigerator. So how can do this? I mean, it's just a metaphor. This metaphor means it basically means it's not very possible. So now how to work around this? So I just introduced 3 restrictions of P4. So now if we want to implement those economy or bitmap on the NFP SDK, now one of the characteristics of NFP SDK is that we can call into C code from P4 program. So if we have this characteristic of NFP SDK, then we can see that we can easily fix those restrictions we mentioned before. So the first restriction is that if statement can only be used in the control block. So now, since we can call C code from P4, call into C code from P4 program, so now we can just go to the action body and we can apply the if-else statement. We don't need to wait until the control block. And the second restriction is then it doesn't support for loop. So now, since we can call into C code, C supports for loop. So this restriction can also be be fixed, right? And the next one is P4 can only support limited set of parameter actions. Now, if we have this characteristic, we can just define, we can have a use-defined parameter action, and we can easily call it. So this is one of the important characteristic of NP SDK. So now I want to give you an example how we can do this by calling into C code in the P4 program. So on the P4 side, suppose now if we want to modify some field in this header or metadata, how can do that? So suppose we now have we have header IP4 underscore T, and we have another metadata called A underscore T, and they are all being instantiated as IP4 and A. If we want to modify some field in this IP4 or A, first we need to use the keyword primitive underscore action, and we use this keyword to define my underscore function. That's first step. And then if we want to use this primitive action, we can just call this action in another action body. It's called action work. So this is the P4 side. I have used the red color to mark them. So then if we go to the C side, so first we need to define, in C side, we need to define this function name as PIF, as protocol independent forwarding underscore plugin underscore my function. We have two input for this function. They are standard, so we just keep them. Then if you want to say, if you want to read some value from this P4 side, first, for example, for this IP4, it has two member fields, source address and destination address. If you want to call them and read them, so first we can define a header. The format of this define this header is by PIF underscore plugin underscore this header IP4, then underscore T. And then on the right side is the equal sign. The last name should also be IP4. So in this way, we can define a header, and the next two lines tell us how to just read those values out from the P4 header. So that is PIF underscore header underscore get and underscore IP4 and three underscores, and then this is the member fields of this IP4 source address. And I'll simulate for next line. So in this is where we can easily read the value from the P4 side, and then we can, after we get those values, we can develop some applications based upon the values from P4. And then the next two lines is used on the metadata. So we have the metadata A. It has a field called timestamp. So first, how to read the value from P4. So we can use PIF plugin med get, and then double underscore A and double underscore timestamp. So in this way, we can get the timestamp from P4 side. And then how to update the value in this metadata. So the next one is metadata set. So we can have PIF plugin med set underscore A and double underscore timestamp. And then the first one is the headers, is the my function input, and the next value is the updated value. We can input any value we want there. So here, just do first we read it as previous, and then increase by 20. So in this way, after we call this function, in the P4 side, this timestamp will be increased by 20. And finally, we need to return a macro. So I think there are two macro. One of them we call a forward. So after, if we return this function as a forward, then we can continue this pipeline. If there's another one called return drop. So which means after this primitive action, user-defined primitive action, this packet will be dropped. So this is one of the important characteristic of NFP. So in this way, you can easily control our program by calling C function. So next, I want to focus on the implementation of economy. So there will be three different kind of variation of economy. The first one is vanilla P4, which is we only use P4 design this economy. We also want to use P4 and C Sandbox to design economy. And finally, there's a cache there, so we want to use a lot. So we have three different implementations. And finally, there's another one I mentioned before, the speed map, but we don't want to go into the detail of the speed map, the implementation of the speed map algorithm. And all the source code now is available at this GitHub. If you're interested, you can take a look. So first, implementation of this economy with vanilla P4. So let me just go back to the algorithm of this economy. So from this flowchart, from left side to right side, we know that we need to maintain some global data structure. The first one is called heavy header. It has its flow information and its corresponding count. And also we need to maintain a matrix. It has 3 rows and n columns. Now similarly, in this P4 program, if you want to maintain such global data structure, so it has the stateful memory, so we can use register. So first, what do? We use register to maintain such a global data structure because it's stateful memory. It doesn't depend on each packet. Then the next is a rest condition, because in this NFP architecture, we know there are a lot of islands, and on each island we have a lot of micro engine, and each micro engine has a lot of threads. So it's a very huge parallel environment. So when we do read and write, we need to take care of this rest condition. So this program introduced can be used to solve this rest condition. And the next one is for safety. Sometimes we better call this pragma natural no lookup application, because in the release notes it says every time when we use this register to control the data flow, it's better to use this pragma to make sure it is correct. Though the performance may be not great, but it can guarantee the result is correct. So here the same. If we want to run this economy, first we need to maintain this global data structure. So for this heavy header, struct heavy header, we have this register HH_R. So we use this one to maintain this heavy header. And for that matrix sketch, 3 rows and n columns, we use this 3 different registers, R1, R2, and R3. And then next, we have 2 metadata. These are used for the transition in and out register. Because in this P4 program, we cannot directly operate on register. So we have to, declare 2 metadata, so we can, temporarily store those values. Then we can operate on that. So this is how we update this in this P4 program. So if we let me temporarily go back to that flowchart. So first we hash each flow, so we end up with 3 hash values. Then we go to corresponding row and column, we read the value, update it, and write it back. Then final step is final minimum and compares minimum with the current heavy header. So now similarly, we can do this in the P4 program. So first we need to hash the flow. So in the P4 program, we can call this P4 primitive called modify field with hash best offset. So we can call this primitive to get the hash values. And the next step is read the value of this register, and then we add it to the field, and then we just do by 1 because we want to. The concern is packet count, and finally we need to write the value back. So we have register write. So that's read, update, and write. So this is how we do this in this by P4. And if you want to complete this P4 program, we know the final step is to find a minimum. And then we need to compare the minimum with the global, maintain global heavy hitter. And we can down those by going through several tables I have shown you before. But that process is tedious level work. So now if we don't want to go through those tedious, table to find a minimum, so we can kind of switch from P4 into C. We can use the C sandbox. So and now we can replace this pragma natural register locked by the memory read atomic and the memory write atomic. So this the purpose is the same. We want to avoid trying to avoid a rest condition. So the before is P4 with C sandbox, but we can see we just use memory read atomic and a memory write atomic to. We know there are three. We need the parameter. We know there's read, update, and a write. We can do that by atomic. However, there's a loophole, which is finally we need to compare this minimum with the heavy hitter count. Now, if this is not a critical section, then we could have a scenario which is probably there are two threads. They all think they are having the heavy hitter, so they are all trying to update this global heavy hitter. So now, if unfortunately this order is wrong, then we can see the final approximate heavy hitter could be wrong. So now, if you want to, the 100% correct updated heavy hitter, how can do this? So which means we have to put this if statement into a critical section. Now in this NFP, we can implement a lock in this way. So first we can declare a lock initialized by 0, and then we can call this memory test set. So in this way, we can make sure that only one thread can go through can get out this while loop and can reach our next critical section. So we can put those if statement into this critical section, so we can make sure that only one thread can update this global heavy hitter. And finally, if we want to unlock, we can write 0 into this lock. So now the next thread can have a chance to do this again. So now these are the basic implementation detail of this counterbeam by vanilla P4 of P4 and C sandbox, and a final with a lock. So next, I want to introduce how we evaluate this performance of the three different implementations. We use two times 40 gig Agilio cards for our performance evaluation. So if we look at this picture below, we can see we have two hosts. We have host A and a host B. Each host has 2 by 40 gig Agilio cards, but we only use one part of that. And then the data is from the host A. So first, if we look at the left side, this host A, you can see this SDN_V0.0. And we have another, this is the virtual function, and it attached to a bridge BR0. And also the physical called SDN_P0 is also attached to this bridge BR0. So on the left side, we run the Agilio OS. So this is why you can see SDN_V0.0. On the right side, on the host B, we run this protocol independent forwarding runtime environment. So I call it PIF_RTE. So on the right side, you can see in default it generates these 4 virtual functions. So I use 3 of them. So first, after the packet get to the physical SDN_P0, we in the P4 program will let the packet go to VF0_0. And then we let the traffic go to the bridge BR0, and then the bridge, there's a flow rule there which follows traffic back to VF0_1. And then finally, the packet will go to VF0_2. The reason why I want to do this because I want to calculate the latency, processing latency for each packet. If you want to use, in the NFP SDK, they have intrinsic metadata that ingress global timestamp. So if you want to calculate the latency, we need them twice. So this is why we need to let the packet get into the PIF RTE twice. So then we can get the entrance time twice. Then we can find the difference. So we can get a not very correct approximation because you can see there's still some time that we will spend on VF0 underscore 0 to BR0 and to VF0 underscore 1. But anyway, since we want to compare 3 different implementations, let's assume that this time is almost the same. So we can ignore them in the next comparison. So we have this 3 different implementations of economy. The first one is vanilla PFO. The second one is PFO and C Sandbox, and final we have this Sandbox with log. So the next row we have its micro engine cycle. So now by comparison, we can see that vanilla PFO has the longest latency, which is 5.7% larger than the PFO and C Sandbox, and 4.8% larger than the PFO and C Sandbox with log. So if we recall in this algorithm, we know that we have those tedious implementation of those tables. So if that is on the pipeline, then probably slow down this packet processing. And then the next, we can see PFO and C Sandbox with log has almost the same micro engine cycle. If we have log, that's 7441. If no log, that's 7376. So it is just only slightly bigger. But you can see if we use this log, we can guarantee that this approximation algorithm is 100% correct, because we can guarantee, since we put this, if the comparison and update into a critical section, we can make sure that the approximate heavy hitter must be the correct one. So finally, I have listed out 2 papers. The first one is about economy algorithm, and the next one is the bitmap algorithm. If you're interested, you can find those papers online, and there's some mathematical proof by probability how these sketches works, and to maintain a good approximation. So we want to thank Open-NFP for providing such a great opportunity for us to introduce our research work. And also, we especially want to thank these people for their invaluable input on the Open-NFP Google group. So this is our talk. Thank you very much.
Thank you, Professor Liu and Xiaoban. This webinar will be available on the classroom page of the OpenNFP.org website. Thank you all for attending.